Good morning, everyone. Myself Jyoti Prasad belongs to EC Department R&D Engineering College. Today, I am going to discuss about quadrature phase shift key (QPSK). So, in the earlier video, we have discussed about binary phase shift keying, how the generation detection was happened, and what's the probability of error. So the important goal of design of digital communication system is reliable performance and effective utilization of or efficient utilization of bandwidth. These are the main motives of digital communication system. So here, how we are going to improve that utilization means with quadrature carrier multiplexing. Quadrature carrier multiplexing. We have two types of multiplexing: QPSK, quadrature phase shift, and the second one is minimum phase shift keying. Like I have shown you, BPSK extension is QPSK, FSK extension is nothing but MSK, minimum shift keying. So what is quadrature carrier multiplexing? Let us say S of t is a waveform, continuous time waveform. It will have two types of components. So in phase component and quadrature component. So that how we are going to represent that in terms of in phase and quadrature means. So this one is I of t, in phase component into cos 2 pi f ct, minus quadrature component into sine 2 pi f ct, which gives a total signal. So if I add in phase, the addition between these two things, so if we combine these two signals s1 of t and the difference between these things is nothing but s of t. See, first we will see about QPSK, how to represent a binary 1 or binary 0 in QPSK wave. So input is binary PSK, input is binary. So if I give a binary value, so it will be converted into a phase among the four values. Like I displayed here, pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. Either it may convert into any one of the phase. The binary will convert it into any one of these phase levels. How to represent that one in equation form? First, Si of t. Si of t is equal to root e by t. Here, two bits we will take. Normally, in the previous BPSK, we have taken energy per bit is EB. So here I will give you the formula E equal to 2EB at the last. Why? Because two bits we are taking. So root 2E by TB cos 2 pi FCT, it is a thing we have seen earlier, plus extra component. So what is this phase plus extra component is 2I minus 1 pi by 4. So 2I minus 1 means nothing but if I substitute 1, it will get pi by 4. If I substitute 2, 3 pi by 4. If I substitute 3, 2 3s are 6 minus 1, pi by 5 pi by 4. If I substitute 4, 2 4s are 8 minus 1, 7 pi by 4. So it will takes any of these four values. So I value is from 1, 2, 3, 4. E is nothing but energy per bit. So where FC carrier frequency is nothing but a fixed integer by t. NC is a fixed integer by time period or bit duration. So this one is in the form of cos A plus B. How we can split this cos A plus B trigonometric formula? Cos A cos B minus sin A sin B. So same way I have expanded this one. That this root E by T is a common thing. Cos A is nothing but this 2I minus 1 pi by 4. B is nothing but 2 pi FCT. You can take in either way, no issues. Here, minus 2 root 2 e by t sin a sin b form we have written. So if you want to represent this one into S11, S12, I need to know the orthonormal basis functions. So previous in BPSK we had only one orthonormal basis function. Here how many orthonormal bases I want to take? I will have a question. So that's why if we see here, so this one is a orthonormal function. See here, so the orthonormal function, so this term and this term root 2 by t. So this term I will take it as phi 1 of t, and here this term and root 2 by t. So this will represents phi 2 of t. So I should take two orthonormal basis functions for the first term separately, second term separately. So I am taking a orthonormal base function phi 1 of t as root 2 by t cos 2 by fct, and second orthonormal function phi orthonormal basis function, second basis function phi 2 of t is nothing but root 2 by t sin 2 by fct. So how can we represent this si of t? The signal cos 2I minus 1 pi by 4 into pi 1 of t. Like that we can represent. So root e, that if I multiply pi 1 of t into this one, the remaining thing is root e cos 2I minus 1 pi by 4. So that takes value pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. Here similarly minus root e sine this term. So you will have four possibilities. Like I say, either 5 by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. Like I said, we will take 2 bits as a pair, which we will call it as dibit. So I have binary 1, binary 0. 2 bits, how many combinations I can take? 4 combinations. 0 0 0 1 1 0 1 1. So what is the phase shift? 1 0. First one I am taking 1 0 with 5 by 4 phase shift. The second combination is 0 0 with 3 pi by 4 phase shift. Third combination is 0 1 with 5 by 5 pi by 4. The last one is represented as 7 pi by 4. So these are combinations. So pi by 4 is nothing but the first one. It will be plus root e by 2. Root e by 2. Root e is the entire duration, energy of the pair. What is the 1 bit duration? Is 1 bit duration is root e by 2. Root e by 2. So SI1 is the first message point of the coordinate, second message point of the coordinate is SI2. So here when pi by 4, so 1 is represented by plus root e by 2. 0 is represented by minus root e by 2. So likewise 0 0 means both minus root e by 2, dt by 2. So 0 1 means minus root e by 2 plus root e by 2. 1 1 means both will be plus root e by 2 plus root e by 2. So this is a coordinate of message points. So how many regions will be there in your signal space? Four regions. Four regions. So the region which represent this point is nothing but root e by 2 and minus root e by 2 is first region. So this is like I said. So first was the first message point plus minus. This is Z1 region, which will have plus minus. One plus one coordinate is positive, one coordinate is negative. So this point is Z1. This is the first message point. The second message point, previous slide, minus minus is here, third quadrant. Message point 2 is minus minus. This is the third quadrant. Next point is message point is minus plus. So this comes in second quadrant. So this is the this one. So plus minus Z3 region. The remaining last one is plus plus, which is nothing but first quadrant. So here that region I am calling as Z4 or message point 4. So these four regions, how can I read? How can I separate? With two boundaries. I am taking a boundary phi 1 on phi 1 as a decision boundary, and I am taking another decision boundary phi 2 which separates four regions. So Z message point 1 in region Z1, message point 2 in Z2, Z2 region, message point 3 in Z3 region, message point 4 in Z4 region. So four regions will be there. So what is the decision rule? Set of points closest to first message point is called associated with first vector Z1 region. Like four rules. So I agree, earlier I told like that. So the S of t we will is a combination. The difference between these two, is nothing but in phase component and quadrature component. So how to represent in phase quadrature means, so the odd number sequence is I am taking as this odd numbers. I am taking the first sequence. So 0. So first one is 0. So as it is, whenever changeover occurs, here the next bit is 1. So phase shift shifted, phase shift phase shift shifted. Here the phase is shifted, and here 1 to 1 no change, so it will continue as it is. Here binary 1 to 0 change occurred, so phase shift will occur here. So this is a odd number sequence. So if I represent all even number sequences, even represent sequences, this is one waveform. So this even number sequence. So whenever 1 to 0 transition is coming, there you will come across a phase shift here, and all zeros, remaining all zeros, no phase shift. So the two combinations will give the x of t, the operation between these two things. So at this particular point, the phase shift occurs. So that phase shift is called quadrature phase shift. The next point where we have change is called this one. Here we have phase shift. So the resultant waveform is called quadrature phase shift keying, where it will take the values among the four values of pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. So the received signal is x of t, like I said previously. X of t can be converted into observation vector x1 like this. So we have two basis functions. So x1, x2 both will come. So if I multiply received signal with phi 1 of t, it will give x1 value. If the received signal x of t, if I multiplied with phi 2, that signal results x2. So this is a transmitter. So like I said previously, if I give input to a demultiplexer, it will convert into a odd number sequence and even number sequence as displayed earlier. So then I will combine both the things, will give QPSK waveform that will be transmitted through channel, and the received signal is x of t, like I said in the previous slide. So x of t, if I multiply with phi 1 of t, I will get x1. X of t, if I multiplied with phi 2 of t and integrate over the limit, I will get x2. So we should take decision rule separately. For x1, separately I perform the decision rule. For x2, separately I will perform the rule. Then I will mix this one using multiplexer. So here again I am telling what technique you implemented at the transmitter, the opposite technique we should implement at the receiver. Here I used demultiplexer, here I should use multiplexer. Then the combined wave is nothing but binary wave. Whatever the input you send, binary will come as it is. This is about QPSK generation and detection. What is the detection rule? What's the detection rule? So x1, if x1 is greater than 0, decision will be taken in favor of binary 1. If x1 is less than 0, then it will take in favor of binary 0. A positive value is binary 1, a negative value is binary 0. Likewise, we will do the detection. So this is about QPS.